So let me start quick because I have only 25 minutes. So this is the structure of my talk. I will give some introduction, some motivation why I want to study this problem about pure spinors with color kinematics. Then I will talk a little bit about 10-dimensional superpyramid in its component formulation and also in the superspace formulation. Then I will study the superparticle in 10 dimensions, the Brink charge version, and also the pure spinor, and we will see how superpyramids emerge from the quantization of these wordline models. And also I will talk about the VGOS a little bit, how we'll construct this object in the pure spinor setting. Also, I will discuss the scattering amplitudes in this pure spinor field theory framework and how color kinematics duality is realized in a simple way in this formalism. Okay, and finally, I will give some conclusions. Okay, let me start quick with the introduction. So I think all of us here know that color kinematics duality is probably one of the most important discoveries that we had in the last few years. And this was discovered at the level of scattering amplitudes and is still not well understood because it's kind of a hidden symmetry from the Lagrangian viewpoint, right? So basically, this symmetry states that if you have a gauge theory scattering amplitude formulated in terms of cubic graphs, like in equation 1 here, it's possible to find kinematic numerators in I satisfying the same relations obeyed by the respective color factor Ci here. So basically, the sum here, Ci plus Cj plus Ck equals to 0 is like the Jacobi identity. So it's always possible to find a triplet of numerators satisfying a similar relation here. Okay, and one of the most important applications of this representation in equation 1 is that we can use the so-called double copy mechanism to compute gravity interactions just by using this, I mean, schematically, by using this replacement of the color factors by the kinematic numerators. Okay. Good. So in particular, for instance, now people are studying the UV behavior of maximum supergravity by using these CK representations of super young means. Good. So it turns out that one can show that this n equals 4, d equals 4 super young means theory can be formulated in a simple way in 10 dimensions. Okay, so in 10 dimensions is just one supersymmetry, and the action is very simple. And also, it was shown that pure spinors can elegantly describe maximally supersymmetric H theories from a field theory and superstring approach. This was done by Berkowitz in 2000 and also by Sederwall in 2009. In particular, for instance, 10-dimensional superpyramids can be formulated in pure spinor superspace as a shared Simons-like theory. So it's a cubic theory. Okay. But we need to extend the ordinary superspace to include pure spinor variables. So in this talk, I will use the cubic nature of this action in order to compute the scattering amplitudes of 10-dimensional superpyramids and see how color kinematics duality is simply realized in the framework. Okay. So let me start with the first part. This first part I will run a little bit because I don't have much time. But basically, what I want to do here is just giving a brief review about 10-dimensional superpyramids. So let me set some notation here. So I have in my equation 2, you can see the action for 10-dimensional superpyramids. We have the field strength, we have the gluino. This nav line is the covariant derivative as usual. These vector indices are important. So let me explain to you. For instance, I will use letters from the middle of the Latin alphabet to denote SO1, I vector indices, and letters from the beginning of the Greek alphabet to denote major and nobile indices. Okay, so they are 16 components. Also, these gamma symbols in equation 2 are basically the SO1, I Pauli matrices, which satisfy this Clifford algebra here in my third point, in my third item here. So this action can be shown to be gauge invariant, of course, but also is invariant under supersymmetry transformation detected by equations 3. Okay, where epsilon alpha is an arbitrary fermionic parameter. Good. So this is the component formulation of superpyramids. As I said, is very simple. If you reduce from 10 to 4D, you basically obtain the n equals 4 four-dimensional superpyramid action. So now let me study the same theory, but now from the superspace viewpoint. In order to do that, I need to introduce a supersymmetric generators. These generators are given equation 4. So using these generators, I can construct the supersymmetric derivatives as in equation 5. And now I will introduce, as we do in the bosonic case, I will introduce this one-form supergauge connection. So the supercovariant derivative will be defined as in equation 6. This is the exterior derivative plus the supergauge connection here. A is a Lie algebra value superfield. And I can also define the superfield strength in a similar way as we do in the bosonic case. Okay, this is given in equation 7. One can show that this F or this superfield F must satisfy the super-Bianchi identities given in equation 8. And in order to study these super-Bianchi identities in components, let me expand the superfield strength in terms of its components. In order to do that, I need to introduce the superfield binds, these fields EAN, EMA, okay? And it turns out that you can show that since we are working on superspace, the torsion is not zero. So there is a component which is not zero. So we need to take into account this, and we basically find that the components of the superfield strength is given by equation 10. So we have the usual kinetic part plus the nonlinear part, but also the term proportional to the torsion. So when we write down this in terms of components, we find these equations 11, 12, 13. So we have the fermionic, the spinorial part, the vector spinor part, and the bosonic part here, or the two-point part if you like. And now we can study the super-Bianchi identities, and these identities basically are given by these equations here from 15 to 18. Okay, all of these components are given in these equations. Now we need to solve these equations in order to see how super-Yang is encoded in this formulation. In order to solve these equations, I need to impose constraints. Okay, one of the constraints is called conventional constraint because it's always possible to reach it by using field redefinitions like this, for instance. Here, I'm just redefining my super gauge connection such that I can satisfy this constraint here. And there is also a constraint called dynamical constraint because this is a physical one. In the sense that this constraint will put the theory on shell. Okay, so if we put both constraints together, we basically have this statement that the whole spinorial component of the field strength must be zero. Now we need to replace this into the Bianchi identities, and we basically find that the Bianchi identities are solved by these equations 22 and 23, where this W beta is the spinorial part of this vector spinor, which is one of the components of the superfield strength. Okay, good. Now we can use the dynamical constraint, and then we basically find the equations of motion in superspace satisfied by the gluon, by the gluino superfield and by the field strength. These are basically the analogs of the equations of motion that the bosonic fields satisfy in ordinary space. So, for instance, we can solve the equations of motion in a specific gauge called the Hartner-Schneider gauge. Okay, and when we do that, we basically find that the theory expansion of the superfields A alpha and A are dictated by equations 26 and 27. This lowercase n is the gluon polarization, and this chi is the gluino polarization. Okay, that's how the super-Yang-Mills fields, physical fields, appear in this superspace formulation. We can compute the action of the supersymmetric generators on the superfields, and we find the supersymmetric transformation that we mentioned in the first part of my talk when we were studying the component formulation of super-Yang-Mills. For convenience, let me rewrite the equation of motion in Lycon gauge because this will be important soon. So basically, I just go to a reference frame where the momentum Km, the only non-zero component of the momentum Km is K plus. And I find these equations of motion here. These AA dot and I are basically the SOA, vial, anti-vial, and vector indices of the superfield A alpha and AM. Okay, and I can do the same thing with the supersymmetry algebra. And then I will show that basically AA is just pure gauge, so it's not physical. So we can set it to 0. And the equation of motion is given by equation 33. Okay. Using similar algebraic manipulations, we find that the other equation of motion is given by equation 34. So we have these two equations of motion. These equations of motion are important because they will appear when we quantize the superparticle in 10 dimensions. Good. So nice. So now let me explain to you how this superparticle story works. So this is the action for the superparticle in 10 dimensions. Okay, this pi n is the supersymmetric invariant. This action is invariant under Worland reparametrization, supersymmetry transformation, and also by this local symmetry called kappa symmetry by Siegel. Okay. So it turns out that this system is constrained, and the constraint can be computed to be given by this expression, the alpha here, and the constraint algebra is given by this expression 38. Since P squared is massless, because this E here is a Lagrange multiplier imposing the massless condition, P squared is 0, that means that the alpha contains 8 first class and 8 second class constraints. Okay. The point is that there is no simple way to separate these constraints out in a Lorentz covariant manner, but we can compute the physical spectrum just by fixing the kappa symmetry. So for instance, if we use the semi-Lycon gauge, which basically states that gamma plus acting on theta must be 0, the action reduces to equation 39, where SA is given in terms of theta A. Okay. Again, we compute the momentum associated to the coordinate SA, and we find that this system is constrained, and the constraint is given by this d tilde A, and the algebra is given by this Bell expression. It's just the identity matrix here. So we can use now the Dirac procedure, and we compute that the Dirac bracket is given by this expression. Okay, so in order to realize this algebra, we need to use the triality properties of SO8, and we find that the Hilbert space is described by two states, A dot and I, which are basically the states in the Lycon gauge of 10-dimensional super Maxwell. Okay, and the action of SA is dictated by equation 41. These are the same equations that we found in the first part of the talk here. These equations here, that's why I said they are important. So that means that the superparticle, when we quantize the superparticle, we are describing 10-dimensional super Young-Mills in the linearized level, or super Maxwell, but in the Lycon gauge. So now the goal is to describe 10-dimensional super Young-Mills, but in a Lorentz covariant manner. Okay, so in order to do that, I will introduce pure Spinor. So basically, as before, we have the superspace coordinates x and theta with the respective momenta pm and p alpha. But now I will introduce these bosonic coordinates lambda alpha, which satisfies this pure Spinor constraint, lambda gamma and lambda must be 0. And W alpha is its conjugate momentum, which is defined to the gauge transformation given by this expression. This is because of the pure Spinor constraint. And also this BRC operator Q equals to lambda alpha, the alpha. This the alpha is the Bring-Schwarz constraint that I already explained some slides before. Okay, so in this pure Spinor framework, the problem of covariant quantization basically is translated into a cohomological problem. So we need to find the cohomology of Q. So in order to do that, let me split this superfield psi into Gauss number sectors. So basically, for instance, psi 0 is a polynomial of degree 0 in lambda, psi 1 is a polynomial whose degree is 1 in lambda, and so on. And let me focus on the Gauss number 1 sector here in psi 1. So I can write psi 1 in this way. So when we impose the cohomology conditions on psi 1, we basically find that these are the equations of motion which these B fields should satisfy. Okay, equation 44 and equation 45. But these equations are exactly the same equation of motion that we found in the superspace description of super Young-Mills. Okay, but in the linearized level. So this is basically the dynamical constraint, and this is the gauge transformation satisfied by the super gauge connection, by the fermionic part of the super gauge connection, of course. Okay, so that's one way of saying that this pure Spinor framework is describing 10-dimensional super Maxwell or linearized super Young-Mills in a covariant manner. Okay, so in order to see that explicitly, we can solve this equation of motion of the cohomology conditions 44, 45. We can use again the Hartner-Schneider gauge, theta alpha must be 0, and then we find again the theta expansion of A alpha, which is defined in this psi 1 superfield. Okay, and we find all of the components, all of the physical states, sorry, of super Young-Mills, A, the Gluino, and derivatives of these physical fields. Okay, but we can also analyze the cohomology on the other Gauss number sectors, for instance, the Gauss number 0, the Gauss number sector 0, 2, 3, 4, and so on. And it turns out that we only find no trivial cohomology in the Gauss numbers sectors 0, 2, and 3. And these are basically the Gauss antifields and Gauss antifield of 10-dimensional super Maxwell in its Batalin-Vilkovitsky description, respectively. Okay. So therefore, the 10-dimensional pure Spinor superparticle describes 10-dimensional super Maxwell in a manifestly superpolytonic covariant manner. Okay. In order to construct a well-defined measure in this pure Spinor superspace and negative Gauss number operators, we will see that these negative Gauss number operators are important in order to invert the kinetic terms in the master actions of pure Spinor superspace. We need to introduce the so-called non-minimal variables. Okay, these non-minimal variables basically consist of these two pairs of conjugate variables here, where lambda bar alpha is a pure Spinor and alpha is a fermionic Spinor satisfying this constraint. Okay, so now we can write the non-minimal pure Spinor superparticle. It's given by equation 49, and the BRC operator is written such that we satisfy the quartet argument or the quartet mechanism. And this means that basically the BRST cohomology doesn't change. So the cohomology of the non-minimal BRST operator is the same as the cohomology obtained by the minimal BRST operator, just with lambda alpha d alpha as in my previous slides. So that means that the whole non-minimal Pires-Spinor superparticle is also described in 10-dimensional supermaxwell. This is some formalities here, so I can construct the measure just by using these tensors here. These tensors can be found in the literature. Basically, it's just some expressions of gamma matrices and also Kronecker deltas. Okay. An important point here is that we need this n factor, which is basically a regularization factor, because when we integrate these variables, we will find some zero mode integrations associated to no compatible sonic and fermionic variables. That's why it's important to introduce this factor n. Okay. So because of that, we need to restrict our integrands to diverges lower than this expression here, lambda to the minus 8, lambda to the minus 11. Otherwise, we need to change the regularization scheme. Okay. Good. So now, by using the antifield symmetry presented in the Pires-Spinor superfields, we can define the anti-bracket in Pires-Spinor superspace, and in the usual way, like we do, for instance, in the antifield formalism, right? And then we can define the master action, like in equations 52. Okay, and when we do that, we basically see that the simplest action that we can construct is given by equation 53, and we can find that this equation describes the equation of motion and gauge transformation of 10-dimensional super Maxwell. So now the question is, how about the non-abelian generalization of this equation? So again, we require that the master actions should satisfy, and we find that the non-abelian generalization, or the simplest one, which doesn't contain explicitly no-minimal variables, is given by equation 54. When we compute the equation of motion and gauge transformation of this action, we find this equation here, 55. When we expand this in terms of Pires-Spinors, we find that these are the same equations of motion and gauge transformation that we found in the superspace description of 10-dimensional super Young-Mills. Okay, so this is the action for super Young-Mills in the Pires-Spinor superspace. So in the superspace containing x, theta, and lambda. Good. So in order to invert this kinetic term here, I need to find the equation which allows me to invert this propagator, right? So for instance, in this case, will be, I mean, the object which will allow me to do that is called the big gauss, and this big gauss satisfies this equation here. So Q and B, the anticommutator of Q and B is proportional to P squared. This was constructed by Berkowitz in 2005. So this big gauss is basically this very complicated function in terms of non-minimal variables, but it can be written in a very compact way by using the so-called physical operators introduced by Sederwall and Carlson in 2011, like in equation 57. Okay, these physical operators satisfy this bunch of equations here. These are basically similar to the equations of 10-dimensional super Maxwell, and the solution of these equations are given by these expressions here, 59, 60, 61, 62. So these are just functions of non-minimal variables. Okay, this will be important when we compute the scattering amplitudes. So for instance, when we compute the action of these operators acting on the Pires-Spinor superfield psi 1, which is lambda alpha alpha, we basically find the respective superfields. For instance, a hat alpha is associated to a alpha, a hat n is associated to a n, and so on. Okay, plus just exact term and some terms which are shift symmetry terms. Good. So now let me say something about the Behrens-Gill currents in order to compute scattering amplitudes. So basically, I need to gauge fix my action. I will do that by using some inspiration from string field theory. So I will impose this gauge condition: B0 psi must be BRC exact. So my resulting action is given in equation 67. So the equation of motion can then be computed to be these expressions here, 68. We have the equation of motion for the superfield side here, and we have the gauge fixing condition here. So when we use the fact that the big gauss is nilpotent, so B0 squared is 0, and we apply B0 on both sides of the first equation of 68, we find this equation of motion for psi in 69. So box is the D'Alembertian, and we have the action of B0 acting on two superfields here. And now we solve this equation of motion by using the perturbative method. So we expand psi in terms of the multiparticle fields. Okay, and then we find equation 71. So we have the single particle superfields are BRC closed. The gauge condition for them is BRC exact, and also we find this equation of motion for the multiparticle superfields. Okay, where SP is basically the generalized Mandel invariant, KP is just the sum from K1 plus 2Ki. Okay. Okay, that means 5 minutes, right?
Yes.
Okay, good, thank you. So Then we compute the scattering amplitude just by using the standard formula here, where basically this product is just the multi-particle superfield associated to n-1 particles with the outer propagator B0 over box strip off, which can be seen like the LSSC reduction formula in pure spinor superspace. Okay. In particular, this vertex operator here, which was already used in the literature a few years ago in the context of superstrings, satisfy this gauge condition here. So B0 acting on VI is BRC exact. Okay, so that means that we can use this vertex operator. So when we use this vertex operator, for instance, for the 3-point function, we reproduce something that we already find in the literature for the 3 matrix external states in the context of superstrings, for instance. For the 4-point function, we can also apply the same formula, and we find that the scattering amplitude is given by equation 74. Okay, in order to compute this amplitude, we need to compute the action of V0 acting on 2 vertex operators. We did that in our paper, and we found that the result is basically given by this multi-particle superfield V12 plus something which is BRC exact. And this multi-particle superfield was also found by Maffra and Schlotterer in 2014 in the context of the open pure spinor superstring. So similarly, we can do we can expand the formula for the 5-point function, and we find this more complicated expression. We also computed the action of the big gauss on vertex operators with this structure, and we found that 3 particle superfields found by Maffra Schlotterer in 2014, and also some contact terms which will decouple from the physical amplitude because they can be seen like generalized gauge transformation terms here. Okay. So they are just spurious terms. So we basically give an argument that we can show this for the endpoint amplitude. So we have a match between our amplitudes computed from the field theory viewpoint with the amplitudes obtained from the CFT viewpoint. And yeah, the only difference is that our kinematic numerators contain these contactors here, which they are not so important if we want to compute these scattering amplitudes in the end, right? So let me just finish in 1 minute. So now I'm going to talk about the Siegel gauge. So the Siegel gauge is basically given by this expression, the big gauss must kill psi, okay, in this way. But the big gauss can be written in a simple way in the pure spinor superspace as detected in this expression 80, okay? So if we use this expression here, acting on these vertex operators, we find these equations 81. So this is the general form for the action of the big gauss acting on vertex operators. So now if we impose the Siegel gauge condition, we basically find this algebra structure here in 82. So if we define this bracket, for instance, x, y, like in 83, the action of the big gauss here on 2 vertex operators can be seen as a Poisson bracket. And this formula here can be seen like a Jacobi identity. So if we pass B0 here on both sides, we basically find this formula here, and this formula here basically can be seen like the Jacobi identity of the algebra here, this algebra 83. Okay. Good. So in this manner, Siegel gauge external states would automatically obey color kinematics duality, and also since B0 commutes with the regularization factor n, the Siegel gauge numerator satisfies also crossing symmetry. Okay, so the Siegel gauge is special in that it allows us to manifest both color kinematics duality and crossing symmetry at the level of individual numerators. Okay, let me conclude saying that the 10-dimensional superjamming possesses a shared Simon-like description in pure spinor superspace. The big gauss plays a very important role in this framework because in order to compute kinematic numerators, we need to understand how the big gauss acts on vertex operators. Also, the standard vertex operators V equals to lambda alpha alpha, which were used in the context of superstring, they satisfy this gauge condition B0 psi equals to Q psi here. And we use the vertex operators to show that the field theory viewpoint reproduces the same scattering amplitudes as those obtained from the CFT pure spinor superstring. Okay. And also the kinematic numerators with the big gauss are related to those obtained from CFT techniques by generalized gauge transformation, and that the Siegel gauge is very important in the sense that it allows us to manifest both color kinematics duality and crossing symmetry. Okay, I think that's it. Thank you.
Thank you very much for your very interesting talk. Do you have any questions? Well, if there are no questions from the audience, can I ask a question? So
I think Sylvia has a question.
Oh, sorry.
Hi, sorry.
Please.
Can I ask? Yeah, sorry. Can I ask a slightly tangential question?
Sure.
I was just curious. So you have these on-shell superfields in the pure Spinor description. Can you do them off-shell as well? And I mean off-shell in the sense of SUSY closure is.
You mean in the sense that this equation is not true anymore?
So in the sense that you include your off-shell and you include the auxiliary fields, which I thought there was some story about the pure Spinor formalism allowing these off-shell closures, which we don't know how to do in the traditional language. But I appreciate it's a bit tangential to what you're talking about.
Yeah, okay. What I can say about this is that yes, it's possible to try to find here all of the bunch of auxiliary fields that you will get by using the pure Spinor measure. But what I can say is that we can do that in this gauge here, B0 psi equals to Q psi here, not in the single gauge. So that means that basically our action will not satisfy color kinematics duality, right? So if we want an action satisfying color kinematics duality already, we need to find this action in the single gauge. I don't know if you understand.
Oh, I see. So for your purposes, you weren't interested. Yeah.
Yeah, exactly.
Okay, thank you.
Yeah, thank you.
Any other questions for Max? Yes, so I could have a quick question. So yesterday we saw in Henrik's talk about how in Chern-Simons theory we can naturally realize a very explicit version of the kinematic algebra. Given that the pure Spinor formalism puts Yang-Mills in the same Chern-Simons-like form, could you explicitly realize a kinematic algebra along Henrik's method in this case for full Chern-Simons? I say for full.
Yeah, I think the idea is very similar. Yeah, because the Chern-Simons formulation, with the C-goes in this extended space is very similar to the pure Spinor one. So yeah, I would say the kinematic algebra is given by this expression here, 83.
I see.
So this can be interpreted as the kinematic algebra.
I see. Okay.
Yeah.
And let me also point out, in the spirit of this conference, building bridges between languages, that the appearance of pervasive importance appearance of the B-goes is very interesting from a perspective of, say, Christian's talk, where he was describing the so-called baby box algebra, in which you also have this H operator, such that you have the algebra that D anticommute H equals box, which is precisely the relation between the Q and B naught.
Yeah.
Mm-hmm. Which is not surprised because both of them were, I think, heavily inspired by string field theory methods.
Yeah.
Just a comment.
Yeah. No. Yeah, nice. Yes, I agree.
I see. Okay.